We're going to continue with chapter 6, and we're going to look at section 6.3, and we're going to talk about the polar form of a complex number and the famous de Moivre's theorem. So I'm sure you might have noticed that typically there is always more than one way in which to represent a given mathematical object. So for example, if you're given a function f, you can represent it by a formula such as f of x is equal to x squared minus x e to the x, or it can be represented by its graph, right? And in this section we are going to introduce a new representation of a complex number, and this representation is motivated by the definition of multiplication of complex numbers, which is cumbersome when dealing with expressions such as 1 plus 2i to the power 10. So if you think about the definition that we have of multiplication of complex numbers, you will see that if we are to employ it on an expression such as this will take forever, and we will see in this section that de Moivre's theorem will simplify that calculation. So we'll start off with the theorem 6.3.1. So if p and q are real numbers, so that p squared plus q squared is equal to 1, then there exists a unique theta, and the theta is between open minus pi to pi closed, such that p is equal to sine theta and q is equal to cos theta. So this will help us in converting a complex number to write it in polar form. So so the proof of this is, since p squared is greater or equal to 0 and q squared is equal to greater or equal to 0, it follows from p squared is equal to q squared is equal to p squared plus q squared is equal to 1, that it also means that p squared is less than or equal to 1, and q squared is also less than or equal to 1. So what it means is p is between minus 1 and 1, q is also between minus 1 and 1. But now, since cos pi is equal to minus 1, cos 0 is equal to 1, and cos theta is a continuous function on 0 to pi, it follows from the intermediate value theorem, and that's theorem A.1.1. So we know what the intermediate value theorem says. It says that they will definitely exist alpha between 0 and pi, such that cos alpha is equal to the q. And since cos theta is strictly decreasing on 0 to pi, there's only one such alpha. Now if p is greater or equal to 0, then let theta be equal to alpha. Then what it means is q is equal to cos theta, and p squared, which we know is equal to 1 minus q squared, is equal to 1 minus cos squared theta, which is equal to sine squared. Now because theta is between 0 and pi, we know that sine theta is greater or equal to 0 if you think about the graph of sine theta. And furthermore, p is also greater than greater or equal to 0. So because p squared is equal to sine squared theta, and we see that sine theta is greater or equal to 0, it means that p is also greater or equal to 0, and so therefore p is equal to the square root of p squared, which is equal to the square root of sine squared, which is sine theta, right? So we have managed to show that p is equal to sine theta. And then if p is less than 0, let theta be equal to minus alpha, then cos theta will be equal to cos minus alpha, which is equal to cos alpha, which is equal to q. And right, so since p is not equal to 0 and p squared plus q squared is equal to 1, it follows that cos theta is going to be equal to q, which is not equal to plus or minus 1. So it means that if we look at the open interval, well, it means that theta is on the open interval. It can be because cos theta is not equal to 1 or minus 1, it means that theta can't be either minus pi or 0, so it's in the open interval, right? So as in the case p is greater than equal to 0, we have that q squared is equal to sine squared. And now since theta is between the open interval is in the open interval minus pi 0, it follows that sine theta is less than 0. Now furthermore, we know that p is less than 0. That's what we assumed. So what it means is p will be equal to the minus of the square root of p squared, which is equal to minus the square root of sine squared theta, which is equal to sine theta, right? And this is because sine theta is less than 0, so we will have that. Now since cos theta is strictly increasing on this interval, on this open interval, there also there's exactly one value for theta between that will give us cos theta equals to q. So we've got this nice result which tells us that if p squared plus q squared is equal to 1, then we are going to get exactly 1 theta that gives us p is equal to sine theta and q is equal to cos theta. Right. And then we've got another theorem, and this is theorem 6.3.2, and it says let z be equal to a plus bi, be a non-zero number, right? Then there exists a unique real number theta, which is between minus pi and pi, such that the real part of z is equal to cos theta, and the imaginary part of z is equal to r sine theta, where r is equal to the modulus of z. So this is just an application of what we've just proved. But yeah, we'll have the proof now. So by definition of the modulus of z, it follows that if I take a over r squared plus b over r squared, it's going to be equal to a squared plus a squared plus b squared over r squared. But we know that this will be equal to 1, because a squared plus b squared will be equal to r squared, because r is equal to the square root of a squared plus b squared, right? So therefore we get 1. Now, so applying the theorem that we just proved, this implies that there exists exactly 1 theta between open minus pi and then closed pi there, so that the real part, which is a, is going to be equal to r cos theta, and the imaginary part, which is b, which is equal to r sine theta. So this will be a over r is equal to cos theta, and b over r, which is equal to sine theta, and then we can write it as that. Right, so that is that, and now we then have a definition, and we have to take cognizance of what we've just proved. So let z be a complex number, then the polar form of z will be equal to, z is equal to r cos theta plus sine theta I if z is not equal to 0. And z is equal to 0 cos theta plus 0 sine theta I if z is equal to 0, where r in this case represents the modulus of z, and theta is a real number such that the real part is equal to r cos theta, and then the imaginary part is equal to r sine theta. And this is just coming from this theorem, right? So that's how we define our complex number in polar form. Then let's look at remark 6.3.4. So it follows from theorem 6.3.2 that for any complex number z, there exists a real number r and a theta, so that z is equal to r cos theta plus r sine theta I. Now, since the sine and the cosine functions are both periodic with period 2, z will also be equal to r cos theta plus 2 pi k and plus r sine theta plus 2 pi k I, where I is any integer that you pick. So that means that there are therefore infinitely many ways in which to express a complex number in polar form. But however, by theorem 6.3.2, there is exactly one number theta which is between minus pi and pi, such that this happens, right? And what we then call this special theta, which is between minus pi and pi, is the principal argument of z, right? So we can express a complex number in infinitely many ways, but we can restrict to have exactly one theta if we restrict the theta to be between minus pi and pi, where this is open and that is closed, and we call that our principal argument, right? So the polar form of a complex number can be interpreted geometrically as the sketch below. So we've got that. So for a non-zero complex number, r is the length of the line segment joining 0 and z in the argand plane, and theta is the angle between the angle formed at 0 by the line segment and the positive real axis, measured anti-clockwise for theta greater or equal to 0, and then clockwise for theta less than 0. So what it's just saying is the angle is measured here. So we've got the positive real axis, and then the angle there, and then this becomes the angle. Or if it's going on the negative, we move from there to there, right? So we move clockwise when it's a negative angle like that, so we get that. And remember, we want something between minus pi and pi, so therefore if we are going there, then that's positive, and then if we are going there, then we take the negative angle, right? So our first example, so we express z which is equal to the square root of 3 plus I in polar form with principal argument. So firstly, we need to find r, and r is the modulus of z, which is equal to the square root of 1 squared plus the square root of 1 squared plus 3, which is the square root of 4, which is equal to 2. Now to find our theta, we then say the real part is equal to r cos theta, so therefore cos theta is equal to r, the real part of z, over r, which is equal to minus 3 over 1. And we know that because we want the principal argument, the theta that we are looking for should be between minus pi and pi, and so therefore theta will be equal to 5 pi over 6 or minus 5 pi over 6. But sine theta of the imaginary part of z over r is equal to half, with theta also being there. So therefore what we want is basically the angle that satisfies the two conditions here, and that angle is 5 pi over 6. So here it's supposed to be theta is equal to minus 5 pi over 6, right? So hence the polar form of z with principal argument is equal to z, which is equal to 2 times cos pi 5 pi over 6 plus sine 5 pi over 6i, right? So that's our example. Now we go on to another theorem, and here we are now defining a new definition of multiplication in polar form, right? So we had the one way we would say a minus AC minus BD or something of that nature. So now we are having a new definition of multiplication, and it's in the form of a theorem. So consider complex numbers z and w in polar form. So z is equal to r1 times cos theta 1 plus I sine theta 1i, and then w, which is equal to r2 times cos theta 2 plus plus sine theta 2i. Then the multiplication of these two will be zw, which is equal to, so the product of z and w becomes just the product of the r's. So we got r1 r2 times cos, and so the angle becomes theta 1 plus theta 2, and plus sine theta 1 plus theta 2i. So that is how we will find the product, and the proof is left as an exercise 6.3 number 3 in the textbook, so you can go and have a look at that. But basically now we've got a new way of finding products of complex numbers that are in polar form, right? And then so we are going to have a remark to just talk about the principal argument and how it might change in this case. So for complex number z, which is equal to r1 cos theta 1 plus sine theta 1i, and w, which is that, in polar form we know that zw is going to be that by theorem 6.3.6. But however, it is not necessarily true that theta 1 plus theta 2 is the principal argument of zw, even if theta 1 and theta 2 are the principal arguments of z and w. And the reason is simply because it may happen that theta plus theta 2 might be greater than pi, so it will be out of the range that we want. We want open minus pi and then closed pi, right? And or if you add them, they will be less than or equal to minus pi, and then they also are not in the range that we want. So therefore there needs to be a bit of adjustment in that regard, right? So that we can have a principal argument, right? And so for instance, if we look at cos pi plus sine pi I, and w, which is cos pi over 2 plus sine pi over 2, then zw becomes cos 3 pi over 2 plus sine 3 pi over 2. This is just attained by these have the r1 and r2 are just 1 1, so the product becomes 1, and then here we're supposed to add the two angles pi and pi over 2, so we get 3 pi over 2 3 pi over 2, but 3 pi over 2 is out of the range of between minus pi and pi, so therefore we end up with a principal argument which in this case becomes minus pi over 2, which is different from what we got just by straight addition, right? And then let's look at another example, and this is 6.3.8. So let z be equal to 2 root 3 minus 2i, and then w be equal to 4 plus 4i, and then we want to find zw using 6.3.6. So in polar form, z is going to be equal to 4. So if you find the r and then the principal argument, it looks like that. Again, if you find the r and the argument, you get that. So therefore zw becomes, so you just make you multiply the r's here, and then you get that, and then you add the angles in here, and then you get that, which ends up being pi over 4, which is that one, minus pi over 6, and it ends up being looking like that. Now using the double angle formula for cosine, we have that cos pi over 2 is equal to root of 1 over root 2 of 1 plus cos pi over 6 to the half, which is equal to that. Right. And then sine pi, which is equal to 1 over root 2, 1 minus that, which is equal to that. And so therefore ZW becomes 8. So now you are multiplying. So because we have found cos pi over 2 and sine pi over 2, we multiply by 16 times 16 root 2, and then you end up with an angle that looks an expression that looks like that. Right. So for now, this is what we will do. We'll continue with theorem 6.3.9, which is De Moivre's theorem, in the next video. Thank you.